So hello everyone, and welcome to the first lecture of for 2024 of our 4240 lecture series. So today we have the pleasure to host Dr. Chiara Saggese. She has received a PhD in industrial chemistry and chemical engineering from Politecnico di Milano in 2015. Then she went on as a postdoctoral fellow on experiments in kinetic modeling at Stanford University. And after that, she actually joined Lawrence Livermore National Laboratory in the reaction dynamics group. The research activity of Chiara spans from the development of kinetic models for conventional and sustainable fuels, and also involve kinetic modeling of pollutant formation in combustion processes. Now, currently in this scenario of transition to a decarbonized transportation system, she's now focusing on modeling soot formation from sustainable aviation fuels. Recently, her research focus has expanded to the investigation of wildland fuel combustion and emissions to inform submodels in large-scale wildfire applications. Chiara, thank you very much for having accepted our invitation, and I give you the floor for the presentation. Thanks.
Thank you very much, Alessandro, for the nice introduction. Hello, everybody. So today I will talk about the kinetics of sustainable fuel and related soot formation. And I will talk about some advances in the modeling of our team here at Livermore and new challenges that we're taking on. So let me start. So first of all, I want to acknowledge our funding. So our work performed here at Livermore was supported by the US Department of Energy through the VTO office, the Vehicle Technologies Office. And also part of this work that I will talk about today is funded also through the Laboratory Director Research and Development Program here at Livermore. We have, with this work, we collaborate with many partners, and some of them are listed here, but we also collaborate with many others. So, and a special thanks to all my team that are listed here. In particular, here I want to explain a little bit the teams. So we are working here at Livermore. There are two teams basically in the physics and life science and engineering directorate. One team, I'm in the chemical kinetics team, led by Scott Vagnon and me and Tanushree Chatterjee, and we usually we develop basically detailed and reduced mechanisms for right now low carbon and no carbon fuels for off-road, rail, marine, and aviation sector, and also kinetic model for NOx, SOx, so emissions, and also pH and soot. And we are also developing entering the contrail formation modeling, so water ice particles. The other team with whom we collaborate is a numerics team led by Russell Whitesides, and they help us to basically create solvers that to run faster simulations. So, for example, they developed the 0K. We also have a surrogate optimizer that permits us to create models, a surrogate model to represent real fuel. And as well, we have an optimizer to reduce optimizer, and that permits us to reduce model, kinetic models, to then that can be run in CFD simulation. So now I just want to give you an outline of the talk. So today I will talk about, first of all, I will focus on the fuel chemistry, and I will talk about our work on oxygenate fuel. In the past year, we worked on C2, C5 alcohols, so we developed the kinetics for these alcohols. And so I will show you what we did in that space. And then I will move towards soot formation, in particular focusing on the soot model development. And I will show some case studies on soot from surrogate components of aviation fuels, like the dodecane isomers, and then soot from actual JTA and surrogates of this conventional and sustainable aviation fuel. Finally, I will finish my talk talking about the new research possibility for soot modeling that in the realm basically of aviation contrail formation, and also to help predicting soot emission from wildfire. So let's start. So here is a picture of a flame, and as you know, combustion, so you have fuel and air, and then there are reactions that are happening. The fuel is burning, and then you have gas phase products that are reacting to each other, so gas phase chemical reactions. And then through these reactions, basically pH, polycyclic aromatic hydrocarbons, are formed, and those are basically the seeds, the precursor for soot formation. And here you can see a picture of like soot, the small particle of nascent soot particle that then over time, basically, and in the flame, this is an example, they grow and form aggregates. So today I will explore, first of all, the transition between vapor and the formation of this particle. So the gas phase chemistry that leads then to the formation of the particle. And usually this chemistry is studied through fundamental experiments, ab initio calculation, and as well with the detailed kinetic model. So I will give you an example. Lawrence Livermore has an extensive palette of surrogate of the fuel components. We develop model for many many fuels, but today I want to focus on the oxygenated fuels, the alcohols. In particular, this was an effort. Here we go. This was an effort that we did in the past years through the co-optima effort. So basically, we studied the ignition and combustion behavior of C2, C5 alcohol, which are that can be blended in neat form. They could be used as neat or also blended with gasoline, basically. Here on the left, you have basically the selection of this of all this alcohol, and then we develop kinetic model and we optimize kinetic model for all of them. And that's basically the size of the mechanism that we are talking about, at least for the alcohols. So to give you an idea, so first of all, we developed the thermochemistry of the various species of the mechanism, and we used also group additivity method. So we developed for each. You can see here the molecule is. There are different groups, and for each groups we have enthalpy of formation, entropy, and heat capacity that is derived from calculation or theory from literature. And then with the group additivity method, you can see here we sum, and then we obtain the thermochemistry for all the species. Second part is basically deriving kinetic parameters for the various reaction classes, and we usually use analogy rules. So these reaction classes are developed based on analogies and also theoretical calculations. This is an example of a reaction regarding pentanol, so the H abstraction reaction by HO2 on pentanol that forms various radicals. You can see alpha, beta, gamma. This is a gamma radicals, and this radical, in dependence of its temperature, can also do the beta scission, and so decompose two different products on the left, or can add at low temperature, for example, in an oxidative environment, can add oxygen and form a peroxy radicals, and then go through the low temperature chemistry. So some of the kinetics of this reaction are well known and are well studied, but some not. And so, for example, for this reaction, the oxygenate addition to the radical, we decided to collaborate with the CU Boulder. And then we explore the potential energy surface, for example, for this, in particular for this reaction, and for the alpha radical, so the oxygen addition on the alpha radical, and then the formation of the peroxy radical, and then its decomposition, basically the favorite pathway, the decomposition to the aldehyde. Then we basically here we added a new pathway, because usually theoretically was only considered in literature with their chemical activated pathway. So we added the pathway with the peroxy, and then we calculated the kinetics at different pressure. We apply, basically, we inserted in our detailed kinetic model, and then the next step is basically validating with experiments. And so these on the right are experiments in a jet stirred reactor at different stoichiometries. Pressure is, in this case, is 1 bar. And this is, for example, the pentanal evolution. So the symbols are experiments. So pentanal is measured in this is oxidation of pentanol. And then the model is are the lines, basically. And you can see how we can well reproduce the data. So this is basically how we do when we focus on fuel chemistry, the different steps that we use. Moving towards the particulate modeling instead. Here, after the particles are formed from the gas phase, they undergoes a different reaction. For example, like surface growth and then aggregation, as I showed before. And so this modeling of this particle, now in this talk, I will focus on soot, but the same approach that we use for soot can be used also for other materials. And so I just want to mention that this is important also for various applications, and some of them I just mentioned it here, and some others I will mention at the end of my talk. Talking about soot modeling, I want to here focus on the new topic that basically we are focusing on at the lab, that is the decarbonization, basically, of aviation, off-road, rail, and marine combustion. Basically, we're trying to produce less emission, and so even the fuels that we use in the transportation, they are changing, and we are mostly focusing on low emission fuel. And so the chemical kinetic model that right now we're trying to develop are in that realm. And here you can see some of them listed, like hydrogen, ammonia, natural gas, and methanol, and on the other side, basically biodiesel, renewable diesel, and sustainable aviation fuel. And my talk basically will focus mostly on these renewable diesel and sustainable aviation fuel and the soot formation from those. So renewable diesel and sustainable aviation fuel, here I put some example of composition of this fuel. On the left, you have example of the SAF, SAF, and on the right side, the renewable diesel. They have high levels of large normal and lightly branched alkenes, as you can see. So the carbon number is in the range C9 to C20, so quite big. And so usually, for example, N-dodecane and isododecane are often used as surrogate fuel components for this type of fuel and their blend. So you can see here their structure, so normal dodecane, and isododecane instead is a very highly branched isomer. And is usually used as a primary reference fuel when measuring certain numbers, but can be used as a component as well for this type of aviation fuel. So studies on soot formation from real fuel are actually limited, and there are many on N-dodecane, but they have typically focused on spray flames and premixed flame of N-dodecane. And also, instead for isododecane, I would say that soot formation studies are quite lacking, and even for blends, received a very few attention. So to understand really the soot formation from this fuel, it's complicated. So our objective for this work was, first of all, to extend the LLN kinetic model to predict also soot formation, and also validate with the surrogate components for SAF and renewable diesel. And also create, we needed new canonical measurements, right, of soot volume fraction from these surrogate components and their blends. And in particular, our focus, and in this talk, I will focus mostly on counterflow diffusion flames, since they are closer to the reality of what combustion, of the combustor, of the real combustion that is happening in various applications. This is again the palette of the surrogate fuel components. So we will focus on, in this case, aviation and diesel fuel and pH and soot. So how we model basically soot particle formation. The LLNL detailed kinetic model for formation of the polycyclic aromatic hydrocarbon basically was extended to predict soot formation and growth. And this developed model, we use the discrete sectional approach with an extensive use of lumping rules to develop it. And so here you can see basically the species, pseudo species that we use to define bigger pH and particles. So the first heavy pH, and you can see the first one is around 20 carbon atoms, is known as coranulin. So we use the fourth section for bins for that. Then we have the first particle, and is usually between 320 carbon atoms. So if we consider a spherical diameter of this particle, 2 nanometer till like 10 nanometers. So these are basically, we consider particle and spherical particle, and then we consider the aggregates that you can see here. So with this species, we have also different hydrogen to carbon ratio, only one hydrogenation in this case. And then for reaction, for the particle, basically the reaction of the particles are considered in analogy to the one to the gas phase chemistry. Following the various aerosol dynamic principle. And so the reaction class can be defined as, for example, there is the ACA mechanism. Here are the reaction class. So ACA mechanism is H abstraction, acetylene addition. So we have that with the bin radicals. Then soot inception. So basically in soot inception, we consider a small gas phase pH and the bigger pH, so bin 1 and 4 interaction, and also the interaction between also the various pH and pH interaction are also included. Then we have surface growth, and we consider surface growth from this particle when this particle react with the pHs and also the bigger bin, so bin 1 to bin 4. And then we pass through model basically the particles, coalescence and aggregation. So in this case, we have particle and particle collision, particle and aggregates, and then the two aggregates, the aggregation itself. So, and then after we develop the model, the next step is basically validating with experiments. So here are some experiments that were performed at UConn from our collaborators. On the left, you can see the setup. So these are soot measurements that were performed in a counterflow flame burner. And you can see the conditions. So this flame is a soot formation flame. This means that the stoichiometry ZST, the stoichiometry mixture, is lower than 0.5, and you can see basically here. Sorry, I wanted to use the pointer. Here we go. Here. And here you can see on one side, basically, the fuel is injected, and is a mixture of normal dodecane and isododecane with the nitrogen, diluted with nitrogen. On the other side, the oxidizer. And these are the condition of the flame. We explore different stoichiometric condition, like of fuel and oxygen, and also different strain rate. And as well, we did some flame with only dodecane, so different mixture, binary mixture of the two fuels. Here you can see on the right the first results. So the symbols are experiments and are for different flames. So endodecan, full endodecan, that is the red one. The black one is isododecan, and in the mid one, the blue one is basically 50-50 of the two. And you can see the peak soot volume fraction as function as the strain rate. As expected, this soot decrease with increasing strain rate. And symbols, so experiments and model have the right, you can see how the trend is taken. These measurements are important because they are easily modeled with this 1D counterflow setup. It can help address basically the gap that we have in soot formation for these components. But going ahead with the results that we got from these experiments, you can see here how the soot volume fraction as function in this case is as function of the x-axis with the 0 that is the stagnation plane, basically. And you can see for the various blends at normal dodecan, the 50-50 blend, and the isododecan. Yeah, how the model also reproduce the trend. The most interesting thing that we found was the fact that the peak soot volume fraction was increasing as the isododecan fraction of the fuel inside the flame is increasing. And here you can see instead for different strain rate. So the blue one is a higher strain rate and the black one is the lower strain rate, around 200 second times to the -1. And also like is increasing, but also the non-linearity of this increase was actually quite interesting. And also modeling wise, we were trying to understand how to catch this trend. Here, quantitatively, the model is higher. So qualitatively is similar to experiments, but quantitatively is higher than experiments. And this reason can be also due to the type of the diagnostic that is used to measure soot. So these measurements were done with LII, laser-induced incandescence, and light extinction. So there are some parameters that are tuned in order to get this data. But yeah, this is where we are now, and we are trying to explore actually with the model the non-linearity of it. And in these slides, I want to show you, for example, some pathways of pyrene formation. So these species that is basically a precursor to soot. And you can see here, this pathway are, so in red, you can see the percentage of the pathway for endodecan flame, and in blue instead, the isododecan. So the pathway to benzene for both flames are quite similar, and they mostly come for these ring enlargement reactions. But then the reaction in this flame from benzene, so you can see, so for the endodecan flame to form naphthalene, it comes from these two pathways, 50-50 in this condition from benzene, and then the other pathway is instead from the C3H3 addition, and the formation of this intermediate is basically led by the C3H3. So instead for isododecan, this pathway is more important. And as well, if we increase, we discovered that if we increase the basically the isododecan ratio inside the flame, we can see how the importance of these pathways of the basically other interaction between C9 and C7 and C9 reaction to form pyrene actually becomes more important. And on the right side, you can see we just plotted some pH. So A1 is benzene, this is naphthalene, phenanthrene, and pyrene. And you can see among them, basically as function as the isododecan ratio, the one that really clearly shows some non-linearity is basically this pyrene. So yeah, this is basically, and also a function of basically soot, similar to the dependency that we saw in the soot volume fraction. moving forwards, like we were interested in the non-linearity, so we went also in literature. We tried to validate our model as well with the literature measurements, and this data that I show here are from a work that was done in KAUST on gasoline mixture. So it was N-heptane, isooctane, and toluene. So these are kind of a reference molecule, smaller than N-dodecane and isododecane, but they have the similar structure, in particular N-heptane and isooctane. And so we were interested to notice that the same nonlinearity was actually seen as well. So this is a peak soot volume fraction as function as the isooctane ratio. So these isoalkyl component. And then we saw the same nonlinearity like experimentally, and even the model you can see here, we also compared with the most updated model in literature, the recent model from Polimi. But you can see also from the data here, the nonlinearity is quite important. Here on the right side, instead, we were trying to explore a mixture, so N-heptane, isooctane, and toluene. And here as well, you can see the soot volume fraction as function as the toluene ratio for the two flame isooctane and N-heptane, and the increase of toluene. But this that is expected, since toluene is one of the precursor as well and of soot. Then in our validation, basically, we started to consider also data, and this is a collaboration with the KIT, the Karlsruhe, data from various fuels. This is ethylene, isooctane, but then at KIT, they also focused on a jet A1 surrogate. And the interesting setup that they have allows basically them to measure temperature, in this case, species, main species, and also pH and soot as well. So we have the whole, basically the whole measurement. So this data in a country flow is still a country flow flame setup. So it permits us to really understand actually the model and the kinetics, what we are using. So here is a comparison, for example, with a full set of data for ethylene flame in this condition of strain rate. These are all soot formation flame. And also for the bigger pH, so here you have, benzene, and then naphthalene, and a heavier pH until soot. And here they measure soot volume fraction with both laser-induced incandescent, so LII, and as well using SMPS, and so with the two techniques. As well, they did this work. Basically, they also measure different isooctane flame, and in this case, they varied the mass fraction in the fuel side. So isooctane maintaining the same strain rate, but varying this fraction, and then they varied the strain rate, maintaining the same mass fraction. And so you can see here the trend, the peak soot volume fraction as function as the fraction of the fuel at the same strain rate, and as expected, it will be increasing. And you see the model like doesn't show the same. In this case, it doesn't show the same trend, but yeah, as expecting, is increasing. And on the right side, instead, the soot volume fraction is function as the strain rate at a fixed mass fraction. As expected, the highest the strain rate, the lower the soot volume fraction. So these data were interesting, and also because they brought us basically to also evaluate the actual mixture. So they proposed a surrogate, and this was done through the Estimate project, an European project. And so they proposed a surrogate for Jet A1 in particular, and this surrogate species that they use, and these are measurements of the actual surrogate. So not of Jet A1, but the surrogate that is made by N-dodecane, as we talked, isooctane, cyclohexane in this case, and 1,3,5 trimethylbenzene. this surrogate here, they measure basically two flame, and now I'm focusing on this one at the higher strain rate and around with the temperature that is around 1760 Kelvin. And as well here, what I want to point out that is this set of data is very useful for the community for us that we trying to understand and develop kinetic models, because we have a sense of like if we are catching the right parameters and also like the right conditions, like a temperature, and also to compare with the main products that you can see here, and then starting with the benzene and toluene, the main precursor for soot, till the bigger species like styrene, till benzene, here's the xylenes, till to naphthalene and phenanthrene, and here this till to arrive to the soot volume fraction. So yeah, this was a nice work for ongoing collaboration. So what we are exploring right now is a collaboration with the UConn and the group of Francesco Carbone. We're trying to model as well canonical experiments in counterflow diffusion flames. These flames are actually different in the sense that they are called a planar mixing layer. So it's a diffusion flame. It can be modeled as a counterflow 1D, but it's actually a different setup. But here, this flame is basically 3 times thicker than a usual counterflow flame. And so it allows easily to measure species, pH, and soot as well. So it's also another setup similar to the one that KIT put together, to measure all the various parameters. And yes, so we are trying to model as well this flame, and in particular the flame doped. So we started with doped flame ethylene, doped flame with isotoric, and so we are doing that right now. Moving towards the real aviation fuel, and like, for example, Jet A or sustainable aviation fuel. So these fuels are, as I mentioned before, a mixture of various components. On the left, you can see for example, the composition of the Jet A here, and is consists of like and paraffin, isoparaffin, cycloparaffins, and as well definitely aromatics. Here I put some data of Jet A, in particular of heavier aromatics, because we were interested especially to try to match the sooting tendency of these fuels. So we need to understand how much in the composition is made by these aromatics or alkene naphthalenes, I would say, in then or cycloaromatics. And here usually 3% in weight is basically formed by this the aromatics and cycloaromatics as well, and these are the sources. We did some experiments in the past in which we also distillate Jet A, and so this is the distillation curve of the jet fuel, the one that we got, and then this is compared to the work of Levstad. But then we tried really to understand what was in the residual, basically the last 5% of the fuel when you distillate out. Really, we were interested in understanding what was inside. And here is a kind of like GCMS. So we did of the various distillation fraction, and as well of the Jet A as received. And here in particular, I put some data related to the naphthalene to show that there is kind of a heavier components that then can be source definitely of the soot, and that they need to be considered when you create a surrogate for this fuel. Here at Livermore, we have a comprehensive tool that permits to formulate surrogates based on a multi-objective optimization. And so, yeah, we optimize and we focus on different properties. As here, there are some. So the HC ratio, the PO volume fraction, initial properties, density, and especially as well the distillation curve, as I showed you, and the soot metrics as well, the YSI. So we try to match all these properties in creating basically the surrogate, and the prediction model that we use are also well validated. Here on the left, you can see the distillation curve calculated and measured, and as well on the right, the yield sootening, the YSI. And we, in the previous work, we applied this surrogate tool for gasoline. Here you can see the latest work on the DOE surrogate for gasoline was a PACE 20, and the representation, like the results of the surrogate emission delays function as temperature, and how we could predict, even with the surrogate of this gasoline, basically the emission delay. We applied it to diesel as well. And here, yeah, you can see the comparison with the data, emission delay data, first emission, and then emission as function as temperature. And then what I want to focus today is basically we also applied it to aviation. And in particular, we're focusing on Jet A as a start. So the POSF 10325, and this is basically the distillation curve. This is what we had experimentally, and this is what modeling we are representing right now. The surrogate that we developed basically is composed by nine species, 9 components, and you can see them listed here with some endodecan, so and paraffin and pentadecan, and then some cycloparaffin and iso. You can see here some isocetane, so isoparaffin, and then definitely the aromatic. And also we try to consider heavy aromatic in the mixture. And here I want to show you some comparison with the data that are available in literature right now on soot formation for aviation fuel. These are data that we took. It was in the same study. These are still counterflow flame, but these were ethylene flame doped basically with jet A. So first of all, on the left side here, you can see the volume fraction of the baseline flame that is basically just ethylene in different condition. This is stoichiometry condition. Right now, what I'm modeling, I'm focusing only on this. And on the right side, you can see the comparison of the soot volume fraction with the basically the jet with the doped one. So the baseline is only ethylene, and then we measure basically at these measurements were done at UConn with the fuel that we distillated. But this is the Jet A as received, and you can see here the soot volume fraction for that flame as function as a distance from the nozzle. Here you can see the Jet A is received and the different distillated fractions. So the 0.60, so that is very close to the Jet A, and instead the 5%, the last 5%, you can see how it increased basically the soot volume fraction. So modeling, we try to use that surrogate, and we run this counterflow flame. And this on the top, you can see the baseline basically. Here are details of the soot volume fraction. The orange data and line is the soot volume fraction as function as the distance from the fuel, and instead the red data and the black data help us because they are OH star and CH star measurements through PLIF that permitted us to really see what was the position to actually use the correct boundary condition in order to predict this counterflow flame. So this was our, and we are close, like quantitatively, the shape of the peak is very similar. Quantitatively, we are a factor of 3 higher with the modeling. But yeah, considering the uncertainty of the measurements, this is kind of pretty good. This is ethylene, and the same you can see here on the right side, the comparison of the baseline flame. So that is the solid orange symbols and solid orange line compared to the dashed orange and the empty symbol that is instead the ethylene doped with Jet A. So those are the data and the simulation, and as well the model predict predict actually the increase the soot. Here I also plotted the data of the residue, basically the residual distillate fraction that is even more sooty. But yeah, to just give you an idea, other nice experiments related to aviation fuel were done as well in Yukon, and here as well we focus on Jet A. These experiments still in counterflow flames and different aviation fuel were studied. So from Jet A, JP5, JP8, and you can see here also some more bio-derived fuel. Right now, like with this surrogate that we developed, we were focusing on Jet A. So this condition, this is the soot volume fraction as well as function at the distance from the full nozzle. And they also explore the effect of the different full mole fraction and oxygen, the stoichiometry, oxygen mole fraction. And right now we are trying to reproduce this. And on the right side, you can see the comparison of our model with the surrogate, with the one that we are using, and the data basically of the soot volume fraction. And this is flames. These are flames that are poor aviation fuel flames, so not is not a doping of like a certain ppm that is like poor. So these are all data sets that are very useful to validate the model. Now I want to kind of like the last part of my talk will be focusing mostly on the new challenges related to this soot modeling. So in particular, first of all, I wanted to talk about the aviation contrail. So modeling soot formation will help us towards modeling the basically ice particle nucleation and contrail. So what is contrail first? Like contrail is the emission from basically the plane, and as you emission that you have in the troposphere. So when the plane is on the cruise, you can have emissions, and basically aviation is responsible for a range of emissions that can affect the climate. And this effect can be quantified through the effective radiative forcing. And here I put basically down a table that represented, like, so with the from the paper of Lee that was just of 2021, basically with this effective radiative forcing, it tells like the positive values that are the red, it tells how much they are, this emission are warming up the atmosphere. Instead, the negative, they represent the cooling. And so here you can see various emissions from aviation, and the contrail series is here, and is a bigger player in basically in this influence, like the in affecting the warming basically of our climate. So for this reason, now the community, like we are moving forwards, and we have funds to study basically its the formation of this contrail, and it all starts from soot because yeah, so basically the main emission that are coming out from the combustor when you burn an aviation fuel, as we talked about, you form soot, and then but at a certain certain height and in a certain atmosphere, then the temperature are very low, and so the particles will activate. They start activating into water droplets, so they react with the water vapor basically in the atmosphere, and then at low temperature and during time, the water droplets, they will freeze and they form these ice crystals. So that they grow, and then at a certain point, then will sublimate. So this is kind of like theory, or like what they think that is happening. And so the soot is a big part of this formation of ice crystal that then affect the climate. So basically, right now we are trying to focus on trying to understand which are the earliest contributors to contrail formation, and also how the interaction between soot and the water vapor in the atmosphere, and so how we can form these crystals, and so figuring out the microphysics models that are related to this ice formation, the contrail formation. Talking about temperature, when I said temperature is that is very low, is because cruise conditions. So here you can see some data that are taken from NASA. That is, they're good to understand basically the variation of temperature as function as the altitude here. You have temperature here, and this is usually the typical cruise height of the plane. And you can see that the temperature is around 200 Kelvin, like it's very, very low temperature, not the same temperature that we use in the combustion modeling. So the first step was to actually, we are ensuring that the model that we are developing, like self-kinetic model with the soot formation, is actually stable at those temperature, basically. And then we can use it to model, like, cooling and mixing processes in the engine exhaust. And here are just an example of collision probability at various very low temperature of various pH inside the model and their interaction. And it's still stable. So it's an ongoing work. We are collaborating with different partners and other labs as well. But it's definitely a big challenge right now to understand how soot really influence the formation of the ice crystals. The next challenge, the other challenge that we are now focusing on, and we got this project funded by the LDRD program at Livermore, is instead related to wildfires. So we all know that wildfires are becoming more and more common. And here, for example, is the area burnt as function as the years, basically in the various years. In the US, the blue bar, but in California, for example, is like the orange. And for 2020 was a worst worst year for fires. And here you can see a screenshot from the observatory of the smoke that basically was all over our area in California. So it's becoming a big problem. And coupled atmosphere and wildfire simulation can actually assist in planning also mitigation efforts for this event. And there are certain modeling needs that basically we can help and we can improve. For example, one is like improving the landscape full characterization and the wildfire risk using the machine learning. So this is mostly like from the satellite to try to understand what is terrain and what is basically terrain or land or which type of land. So trying to use kind of a machine learning to basically better understand the images and the various of the land, the various fuel basically in the map. Another modeling needs is definitely using chemical combustion codes to better characterize spread and emissions in both natural and urban environments. So the wildfire, they spread from the natural environments to urban environments. So they spread and they burn basically material that can be biomass on one side, but also like urban material kind of. And so it's important. So from the combustion background, so this is where we are trying to help, like trying to understand really how fast a certain material is burning, and also the emissions related to it. And also there are some other as well needs in, for example, the methods of immersive boundary methods to capture actually the terrain, the steep terrain or urban structure to better model how the wildfire spread. In this case, for you can see here for fire spread and like emission to model that is definitely a multi-scale problem. And here you can see where like there are 0D experiments and 1 and 2D experiments where we can actually, with these experiments, we can actually try to create a detailed and semi-detailed chemistry, I would say, and validate with these experiments that are mostly like, for example, TGA experiments and fundamental gas phase experiments, or 1 and 2D modeling, like and are related, for example, to single particle combustion experiments. And with these experiments and simulation at the millimeter and centimeter scale, we can actually create and validate certain detailed and semi-detailed kinetics that then will be important to feed and to help like the understanding of what is happening actually at the meter and kilometer scale. So where other type of model like 3D fire model, and so for example for large fire tests, and then in this case like CFD CFD simulation are run to try to understand how the fire spreads and the emissions, or really full-scale fire simulation that are coupled actually with meteorological models. At this scale, only correlation-based models are used for fire spread and for emission. So, and this correlation usually are based on empirical data. So this is why where we can kind of help, and with this project we are trying from detailed and semi-detailed kinetic basically to help establish this correlation that are then used to inform the subgrid models in this large scale model. This is, for example, a slides of the project that we are actually working on, and in collaboration with the San Jose State University. And we are trying to establishing a framework of simulation of gas-solid interaction in actually a simple geometry, and that can be used for various combustion regimes. So for wildfire, we know that there are regimes like flaming, definitely pyrolysis, flaming, and smoldering. Smoldering is when there is no flame, but the fuel is still burning. So for that, there are no idea of like emission factors or correlation are very poorly understood. And so having something that is kind of like simple in geometry and that can use the telekinetics can actually help for extracting burning rates and pollutant and soot formation, basically information from this fuel. So what we are using right now is basically a numerical code to basically study in this case, we are focusing on biomass, so biomass combustion, ignition, and as well as smoldering behavior. We couple with the detailed kinetics, and then we are validating with the various experiments. Experiments here, I have to say, that are quite lacking. So we don't have much experiments like we have for the gas phase or liquid fuels of species or and speciation measurements or soot measurements are quite lacking. And so But we found some, so we have some collaboration with the CU Boulder and as well Stanford, and we are trying to validate our framework through that. It's still a single particle based model, but we have the possibility to resolve the particle and the fluid around. And with this, when we get this data, then the objective is basically to create a new algorithm, a new correlation for this subgrid model, in this case, our emission model and fire spread model, that are inside the big large-scale wildfire model that is called the WRF Fire Chem, that is a weather research and forecasting model. So there is the meteorological model that is coupled with the fire spread model and with the chemistry. And these are, for example, some results of this model when it is run. Like it can predict the fire emission area and as well the particulate matter if certain submodels are used and are present. So yeah, this is it. This is basically what we are working on right now. And this is the end of my talk. Thank you. And if you have any question, you know.
Okay, thank you. Thank you. Thanks a lot, Chiara, for this very interesting presentation, interesting talk. And I now open the Q&A session. So if you have any question, please feel free to raise your hand and I will and ask them. Okay, if it seems that so far there are no questions, so I will ask a couple of them. So you show that there are still some gap in catching soot formation for especially for these practical fuels that are used in that are planned to use, especially sustainable aviation fuel. How can this gap be like a field? It's a matter of adding more pathways, but in the same time, adding more pathways might mean that you have to consider more kinetic parameters with their uncertainty. It's that, or is the fact that with the uncertainty that we have in the parameters, the kinetic parameters that are already in certain mechanisms, we are able to fill this gap by characterize better those parameters. And
yeah, so no, that's a thank you. That's a very nice question. And yeah, so that's a big an important question, because actually these real fuel are very complex, and from the modeling point of view, we can keep adding like pathways and think about how we can reach a certain to understand better how the soot forms, and definitely, but we need the experiments as well to understand better, and like especially for aviation fuel, I would say, and even the components, the main components of the aviation fuel, we don't have a lot of data that we can actually rely on. And so that will be, I think, a first step, if an effort from, yes, the modeling, we have the tools, and we also can measure like uncertainty of our parameters. So even already what we have, I think it's good enough to tackle this challenge, but definitely having experiments that are well with boundary conditions that are well defined, and also like having not only soot, it's hard, it's more complicated, but having like the full idea of like the various parameters of temperature or speciation, or even the species that are definitely then nucleating soot will be already helpful. So I think this is really a joint work. and the uncertainty there is in the experiments and in the modeling too, so we can quantify that. But I think that more data in this topic that will be for this fuel that will be very helpful, and in various conditions we would really understand already with the model that we have right now that seems to work, but like we will understand what are the limits as well of this model, and if we can actually compare with data, that will be very helpful. Yeah.
Okay, thank you. We have a question from Tarek, so please unmute yourself and feel free to ask it.
Yeah. Do you see me?
Yep.
Yeah.
And
Yeah,
we
yeah.
can hear you too.
Hi.
All right. Thank you very much. Thank you very much, Chiara, for the very nice and very rich presentation. Indeed, it's extremely rich. I really enjoyed it. Well, my name is Tariq Beji. I am from Ghent University in Belgium, and I'm particularly interested in soot modeling for fires, fire-driven flows, basically. My first question is about the validation. You were talking about validation. Do you use axisymmetric laminar diffusion flames? Because you seem to focus essentially on counterflow flames. Is there a reason for that, or so do you use laminar flames?
So counterflow flames, we basically use it for validation mostly right now for the aviation soot formation from aviation fuel. For the fire instead perspective, if you are interested more in that, we are instead targeting more. So we are using CFD tools like a 2D modeling, and so we are trying to model kind of like single particle experiments. So it's and this particle is basically inside a chamber where there is air, and then they increase the atmosphere. So it's and they measure, sometimes they measure temperature and mass loss, and as well there are certain measurements of species, but are very few. So that's but no, like right now I didn't find counterflow flames for like solid fuel. We are actually talking in the community where we're trying to see if there is a possibility to set up a kind of a canonical experiment to measure kind of emission from solid fuel combustion that is easy to model, right? Because if we use such a detailed model, we will need like a simple geometry. But no, right now we are focusing mostly on single particle experiments and also cone calorimeter experiments. That's what we are focusing on to try to.
All right, thanks. A second question that I have, if you allow me to,
Yeah.
is about turbulence. In the modeling, I understand that your focus is on chemistry more than turbulence, but what do you use, in fact, for turbulence chemistry interactions? Is there a specific framework you're using, or?
Right now we are not addressing that. Like for the fire, we are really at the simple stages, so it's kind of like only LES, like it's a full resolved model, but it's only LES. We don't resolve any the turbulence like specifically. We're mostly focusing on the chemistry right now. So it's very simple.
All right, thank you very much. Thank you.
Okay, thanks.
Thank you, Tarek, for your questions. Are there any more questions from the audience? If not, I will just the final curiosity. Yeah, when you have this big mechanism, how hard it is to optimize them, to reduce them so they can be used in in LES or in CFD.
Yeah, CFD. So to reduce them, like we use different methods, but it's not as easy, especially it depends on the application, right? Because we want to reduce it for like if it's for CFD aviation or even for fires, then you need to target the species or to target really like what you are interested in or what you want to maintain from the detailed model. So it's not easy. We have some tools in-house that we are trying to use and optimize here at Livermore as well. but yeah, it requires a lot of, from the point of view of the user, of who is reducing, a lot of like deciding the species that we are interested in, especially if you are interested in a certain type of emissions, and so have the pathways, or the range of applicability for sure, like it influences that.
Okay, thank you.
Thank you.
And
Thank you
I
very
think
much.
if there are no more questions from the audience, we can close this session. And thank again the speaker for, like Tarek said, a rich talk. And thank you also for accepting to present at an early morning for you in California. So thank you again. And yeah, I wish you all a nice weekend, and I'll see you next week for a new appointment of this lecture series. Thank you, everyone. Take care. Have a nice weekend.
Thank you. Thank you, Salvatore.
Bye.
Bye.
Bye-bye.